Now you'll have the case 2, which says one fluid mixed and other unmixed. If one fluid is mixed and other unmixed, let us say this is TCI, so this will be TCE, THI, and this will be THE. So this is the fluid, this is Y and this is X, right? So this fluid is coming in this direction and this fluid is mixed. So mixed means to say you will get on the other side as a constant temperature of Tc along the width. And if this fluid is unmixed, then you will get the again this is area B into L, right? Here the TH is a function of X and Y and Tc is a function of X only, because in this cold fluid will be mixed with this layer, will be going into this direction, this layer will be going into this, so this fluid here will be the mixed fluid. And the case 3, you will get both fluids are mixed. So if the both fluids are mixed, then what you will get? You will get one fluid and another fluid. So you will get the constant temperature on this side, right? So here this Tc is a function of X and TH is a function of Y. Right? Now, if you have to get the solution of these three cases, so there is a special way to do this. If you integrate for these three cases of cross flow, so the result are presented in the form of correction factor, that is F. Now, why we haven't analyzed this? Because this is not in your syllabus, but still I am giving you the brief of this cross flow, that if these kind of situations come, then how will you able to solve those kind of questions. So F is nothing but it is delta Tm of cross flow upon delta Tm of counterflow. Means if you are able to calculate this delta Tm for counter flow which we have derived earlier, that is delta Ti minus delta Te and ln of, right? And if you multiply this with the correction factor, then you will able to calculate the delta Tm of the cross flow. And if you get the delta Tm of the cross flow, you can easily calculate what should be the Q in case of these cross flow situations. Now why we have taken the counter flow? Because for given values of THI, THE, TCI and TCE, this delta Tm for the counter flow, right? This is CF is counter flow. Counter flow is the highest among all flow arrangements, right? So the value of this F will always lies between this, and if you have to calculate U, you have QA of delta Tm cross, right? So you can easily write it as, it is nothing but FUA of delta Tm for counter flow, right? So by this way, by calculating this F, you will be able to calculate the value of Q in case of cross flow. Now how will you plot this F? F is being plotted, F is plotted as a function of two parameters, that is R and S. We are saying R and S. This is a sum notation given to these. Right? So what is R? R is T1I minus T1E upon T2E minus T2I, where 1 and 2 represents fluid 1 and fluid 2, inlet and the outlet, right? So S is which is the second fluid inlet and outlet and inlet upon the first fluid inlet and the second fluid inlet. Now these two fluids, whether we have to write H or C, let us see how we can define these two fluids. So the subscript 1 and 2 corresponds to the two fluids for case first and third. First case is what? When both fluids are unmixed. And third case is what? When both fluids are mixed, right? So it is a material that which subscript corresponds to the hot side and cold side. So you can represent like this, or you can represent like this. So both the situations will be true. But however, for case 2, which says when one fluid is mixed and other unmixed. So in this case, the unmixed fluid will be as treated as 2 and the mixed fluid will be treated as 1. Getting my point? So the parameter, if you take the values, so the parameter R and the parameter S, it is the rate of change of temperatures of the two fluids, where R is always by like this and S is the ratio of change in temperature of the one fluid and the difference of inlet temperatures of both fluids. So that means S will be always like this. Now let us show me how is this you can find the correction value. You have a graph which is being plotted between S and F, where the R lines should be like this. So once you calculated this R, right, and once you calculated this S, so the intersection of these points will give you the correction factor. And once you get the correction factor, you will be able to calculate the Q in this. Now there are two special cases which may come in the heat exchangers, that are the special cases where maybe the situations will be like this. Right? Which means if this is the value, which means TH minus THE will be 0. In this case, it is TCE minus TCI is equal to 0. And if you see this, in the first case, it is when the inlet and the outlet temperatures of the hot fluid will be same, and in this case it will be same, right? So if this is the case, you can say that this is a problem which relates to the phase change. Phase is changing from, let's say, the first case. If you say the case A, okay, it is a case of when you get the situation which will be like this. So this is inlet and this is exit, and you will have the situation, right? So this is your TCI. Clear? And second situation will be is like this. Now first situation, you can call it as the saturated vapors condenses. In case B will be the saturated liquid evaporates, right? Now this mean temperature difference in these cases is same whether it is a parallel flow, counter flow, and the across flow situations. So by this we have done with the LMTD for parallel flow, counter flow, and the cross flow situations. So in the next lecture we'll take up some numericals based upon these situations.